Brain tumors are a form of cancer that affect thousands of people around the world. What cancer is it's basically a bunch or a clump of cells that go in different parts of your body, but they don't have any direction. They don't have any purpose for being there. And for this reason, it's imperative that you get them out as fast as possible. So when it comes to brain tumors, radiologists and doctors usually perform something called an MRI scan. And this gives a better understanding of where these cancer cells or brain tumor is located in order to perform treatments such as chemotherapy and radiation treatment or brain surgery to kind of get rid of them. So when there are smaller areas or smaller brain tumors in the brain, you can usually perform chemotherapy and radiation treatment, which gets rid of them. But when it comes to the larger brain tumors, the only way to get rid of it is through brain surgery. Unfortunately, brain surgery has a cost of its own. It's extremely hard to be successful in. The reason for this is simply because the brain is way too delicate. The smallest area of misconception as to where the actual tumor is located compared to the brain itself could result in total catastrophe. Because the brain surgeries are so hard to be successful in, it makes the segmentation of the actual brain tumor very, very imperative. This reason was why I wanted to create a model that could look at an MRI scan and accurately segment the brain tumor from the MRI scan to be a second-hand tool for radiologists and doctors to use when actually segmenting it from the MRI scans to perform the surgery, overall increasing the success rates of these brain surgeries with better segmentation. To do this, I started researching into the types of models that are used to try and segment any portion of the image, and I came across two main networks, especially used in the healthcare department: MRCNN and UNet. Now, these two architectures are actually quite different, because MRCNN is made to predict multiple instances, whereas UNet is made to predict only one instance. What this basically means is that if I were to give an image to a MRCNN model, it could predict multiple instances of brain tumors or multiple areas of brain tumors. Whereas if I gave that same image to a UNet model, no matter where the tumor is located, it would only show one tumor. For this reason, I decided to go with MRCNN, since I wanted to be able to create a model that could predict where tumors are located and if they're separate or not, because that would be more helpful in surgery rather than if it was just one tumor. I also used this because I had 3D images, and so multiple instances would be more accurate compared to a one instance. Furthermore, when looking into research papers already performing this same task, with just looking at the comparison of different models, I realized that MRCNN had more potential in improving rather than UNet, which is why I wanted to experiment more with the MRCNN. I hope to use UNet in the future. Once I had decided that I was going to use a MRCNN architecture, I started looking more deeper into the methods in the computer science field and the radiological field to see what I could implement and what I could bring new to it. This is where I came across image subtraction. This should not be confused with the computer science version of image subtraction, which is a way to kind of normalize the image. But rather, this image subtraction is a radiological method that radiologists and doctors perform when actually examining these MRI scans. So how image subtraction work is because they take multiple MRI scans, some are enhanced and some are not enhanced. In my case, the ones that are enhanced are the T2 enhanced or T2 flare and T1 enhanced, and the non-enhanced images are the T1 weighted and T2 weighted. And basically what image subtraction is you're taking your enhanced and your non-enhanced and subtracting it from each other. And what this output creates is an image that is more insightful and more valuable and richer in information compared to these normal images. Why this works is because when I say an enhanced image, basically what this means is I'm taking a non-enhanced image and each pixel is enhanced by a certain amount. But the cancer cells, the brain tumor cancer cells, are more enhanced than the ones surrounding it. So when you perform this image subtraction of taking these enhanced images, or enhanced pixels compared to the non-enhanced, and give this resulting output, it's so much more valuable as to where the actual tumor is located. When looking into current research papers to see if this was already being used, I noticed that this piece of information was not being used in these kinds of models, and I realized that this had a lot of potential. Since already radiologists are using it to perform and find more accurate representations of the brain tumor cancer cells, it could also be quite useful in MRCNN because CNN is known for looking for high-tech or high patterns, and this is a really big one. And so when I started using image subtraction in my model, I saw a significant growth in all performance or all metrics. Aside from image subtraction, though, I performed many other experiments. The main one I focused on was inside the architecture of the MRCNN. So how MRCNN works is that, given an image, it goes through a convolutional neural network. And this convolutional neural network is usually pre-trained on a dataset. The dataset that was mostly used for MRCNN and segmentation models was called the COCO dataset, which is a very famous dataset in the machine learning field. Unfortunately, I realized that this would not be very helpful for this specific problem since the COCO dataset doesn't really have anything quite relevant to the brain tumors. Because what the COCO dataset consists of is basic images like cats, dogs, trees, which you can tell doesn't have much similarity to brain tumors. For this reason, I switched out the COCO dataset to a pneumonia dataset that I found on Kaggle. I realized that this pneumonia dataset is a lot better for it to train on because it has a lot more similarity to the brain tumor identification or segmentation, since how pneumonia is detected is by looking for abnormality in the X-ray, and how brain tumors are segmented is also looking for a bit of abnormality in the X-ray or the MRI scan. And so because there's a more correlance and relevance between these two data sets, it would be more useful for it to train on. Regarding my results, when I performed this switching out of the pneumonia dataset and the COCO dataset, I saw an increase in performance in all metrics, including recall, precision, F1 score, and area under curve. When I performed the image subtraction, I saw another great improvement. In fact, my T1 network went from a 0.63 mean of recall to a 0.71 mean of recall. And recall is simply the performance or how accurate the real predictions are, which is what's more important in this kind of scenario, which I am happy that it improved in. In precision, the T1 network, which is basically trained on the T1 images, so T1 enhanced and T1 weighted, that model improved from 0.62 to 0.64 in precision. And overall, the F1 score improved from 0.63 to 0.68. Similarly, in the T2 network, my recall increased by 0.10, going from 0.67 to 0.77. In precision, it went from 0.63 to 0.66. F1 score went from 0.65 to 0.71. I would like to point out that these models do have a constraint because due to the lack of time and the lack of resources, I wasn't able to train these so high compared to these models that are already on the internet. What I mean by this is each of my models were trained roughly around 5 to 7 epochs. But most models should be trained around at least 20 epochs to get a little less than overfitting. But my models were not able to reach that because these models took around 24 to 48 hours just to train on one epoch. And you can realize how long of a time that is for the number of experiments I performed, because sometimes there was errors, sometimes I needed to redo something because there was a small coding fixing in the actual code, or I simply wanted to perform more experiments to see which one was a better fit for the model and which one would be better overall for the prediction and segmentation of brain tumors. And because of this, I wasn't able to perform such high and get such high results like already on the internet. But at the same time, I would like to say that These models, or the goal of this project, was not to get the best possible performance, but instead to see if image subtraction would truly work how I expected it and improve the overall performance of the model, which it did. And if this method were applied to current state-of-the-art models predicting brain tumor segmentations, it could have a totally different future and actually be implemented in the field. Thank you for listening.